We're going to have Josh Pfeffer talking about external DLA and a spanning tree-weighted random planar map.
Thanks, Ewan, and thanks to the organizers for putting together this wonderful conference. So today I'm going to talk about some joint work with you and Gwyn about a particular random growth process on a graph called diffusion limited aggregation, or DLA. And for those who know the difference, let me just say now, throughout the talk I'll be talking about external DLA. So how do we define this random growth process? Well, here I'm depicting it where the graph is Z2, and you start from a single vertex, and at each step I add an edge to my growing cluster according to a harmonic measure viewed from infinity. So I have my first edge, then a second edge adjacent to the first, third edge adjacent to the existing cluster, and so on. And I get something that looks like this, where in this simulation the edges are color-coded according to the times those edges were added. And so this is a model that was originally introduced in the physics literature to describe many random growths in nature. And physicists have studied this model quite extensively. My advisor, Scott, likes to demonstrate this by pulling up an archive page and just, Google Scholar, and just searching for DLA. And as you can see there, you get a lot of hits. And so physicists really care about this, and they've studied this extensively using simulations. But if you actually look at what's been proven rigorously mathematically about this process, the results are quite limited. So there was a famous result of Keston, where he looks at the external diameter of the DLA cluster after n steps. And so that just means like the maximal distance between 2 points in the cluster, where I'm measuring distance in the ambient graph. So for Keston, the ambient graph was ED. And he bounds from above the growth rate of this external diameter. But I mean, these bounds are far from optimal. And this is more or less all we have in terms of rigorous results about two-dimensional DLA, as Schramm noted 12 years ago, and this statement has stood the test of time. And so in our work, we're going to look at DLA, but instead of looking on some deterministic lattice, we're going to look at DLA on a random graph. In particular, we're going to look at DLA on an infinite volume spanning tree weighted random planar map. And our result shows that in this particular environment, we can prove the existence and value for the growth exponent of the external diameter of the DLA, and that growth exponent is going to be 2 divided by d, where d is the fractal dimension of square root of 2 Liouville quantum gravity, in the sense that Ewan described in his talk yesterday. And so in particular, using those strong upper and lower bounds that Ewan presented yesterday from his work with Jean Ding, we have numeric upper and lower bounds for this growth exponent of the external diameter. As you can see, they're pretty close to each other. And of course, if we believe Ewan's semi-joking, semi-possibly serious conjecture for the value of d gamma for general gamma, then of course we have an exact value for this external diameter. Okay. So for the rest of the talk, I'm just going to outline the 3 main ingredients that go into the proof of this result, and then I'll briefly sketch how you put these ingredients together. So the first ingredient we'll use is an observation that follows from discussion in Scott and Jason's work on QLE, which is that in this particular random environment, we have this equality of loss. So if you run your DLA cluster for n steps, and you look at the complement of the cluster, that map will have the same law as if you run a loop erase random walk for n steps and look at the complement of that. And I'll show you how you can see this equality of law in just a moment, but first let me just mention the other 2 ingredients that we'll use. So this is something Jason described last week, and Guillaume mentioned in his talk, and others, and so I'll just say quickly what Mullins bijection is, and in particular I'll point out how Mullins bijection not only encodes my random planar map in terms of walk on Z2, but also encodes a suitably coupled loop erase random walk to infinity in this walk on Z2 in a manner that I'll describe. And then the third ingredient is, of course, where this dimension d actually shows up, which is that d arises in 2 particular geometric quantities associated with our random planar map. And I'll describe that as well. Okay. So let me first describe this equality in law. Okay, so I'm going to show this for a finite random planar map, but you could easily extend this to the infinite volume case. So here we'll measure a harmonic measure from this black vertex, and we'll start growing our DLA, or loop race random walk, from the blue vertex. Okay, so now let me put DLA aside for just a moment and think about growing a loop race random walk from the blue vertex to the black vertex. So I'll grow it for n steps. In this example, n will just be 4. And one way of describing the law of this segment of the loop race random walk is to look at a uniform spanning tree on the spanning tree weighted map, looking at the path in the tree from the blue vertex to the black vertex and taking the first 4 edges of that path. And this will have the law of the first 4 edges of a loop race random walk. Okay, so now if I want to look at the complement of this red path, I can sort of think about thickening this path and kind of turning the thing inside out. I get this. And I think about what the law of this map is, but for now I also keep track of 2 extra pieces of information, namely the black spanning tree and this blue vertex. So the law of this triple is just going to be, well, the law of the map tree pair, where the map is a uniform random planar map with the right number of vertices and with boundary of length 8, which is double the length of the original red path. And the tree is a uniformly chosen spanning tree on that map where we have these like wired boundary conditions. Okay, and then the blue vertex, well, its position will be determined once we have the map and the tree. Because if you look in the original map, if you look at the path from the black to the blue vertex in this map, and you look at where it hits the red path, it'll be at the tip of the loop race random walk. And so if you look here at the path from the black vertex to the boundary in the tree, it will hit the boundary at the point exactly opposite the blue vertex. So we can describe this law explicitly. Okay, now I haven't mentioned DLA yet here, but in fact we're almost done. And now we can show this equality in law by an inductive argument on the number of steps I take. Okay. So let's say I know that for, if n equals 4 steps, that the law of this map, given by the complement of the loop race random walk, for getting the tree in the blue vertex, is the same as the law of the complement of a DLA cluster run for 4 steps. And let's think what happens when I now grow for a 5th step. So if I think about growing my loop race random walk for a 5th step, if again I define this loop race random walk as coupled with the tree, well, it'll just be this edge over here that I now highlighted in red, or corresponding to this edge over here. And now if I just forget the black tree and the blue vertex, and I think about what that unconditioned law of that new red edge is, well, by my description of the law of that map tree pair, it's just going to be an edge chosen from those edges adjacent to the boundary from harmonic measure as viewed from the black vertex, which is exactly how I grow my DLA. And so that completes the inductive argument, showing this equality in law. So that's the first ingredient that I'll use. Now the second ingredient I'll need is Mullen's bijection. So let me just review that very quickly. So this is a depiction of part of an infinite volume spanning tree weighted map with a uniformly chosen spanning tree on it in red. And of course it doesn't look like a tree in this picture because we're not seeing the entire map. And the root here is in black. Dual root will be this face. And so we can draw the associated dual tree on the dual vertices. And then we can add these green edges between each dual vertex and the vertices on the corresponding face. And now the red, blue, and green edges together form a triangulation where each triangle either has 2 green edges and 1 red edge, or 2 green edges and 1 blue edge. Now we can look at the path exploring the interface between the tree and dual tree, and this encodes a walk on Z2, where if my path is visiting a triangle where it's visiting a red edge for the first time, then I'll increase my left coordinate by 1. If it's visiting a blue edge for the first time, I'll increase my right coordinate by 1. And if it's visiting a red or blue edge for the second time, then I'll decrease the corresponding coordinate by 1. Okay, so this is probably something that almost everyone here is familiar with already. But let me just stress that we can also see the times this exploration path traces a loop race random walk, where we define the loop race random walk as being the infinite branch of the tree, of the red tree. We can see the times that my exploration path traces this infinite branch very easily. So of course each edge gets traced twice, so let me just characterize the times in edges on the infinite branch are traced for a second time. And it's not hard to see that these times correspond to record minimum times of the left coordinate process. So you see these branches off the infinite branch correspond to these sort of excursions away from this running minimum process. And of course I haven't depicted those times in which I trace blue edges, but those will just correspond to times that my left coordinate doesn't change at all. So this characterizes the loop race random walk in terms of this walk on Z2, which will just have the law of a simple random walk on Z2. And this will be important in our analysis. Okay, so finally, this third ingredient that I will use is, well, where this dimension D actually appears. So the first place that D appears is in a theorem by Yuan and Jianding, which is that D is going to be the growth exponent for a metric ball in the random planar map centered at the root. Now the second place where D appears is in this theorem, which, I mean, you may have noticed doesn't contain D at all here. But so this theorem is now saying that if I look at a set of triangles, remember Mullen's bijection, my exploration graph is tracing these triangles and that triangulation. If I look at a set of those triangles traced in a time interval of length n, deterministic time interval of length n, and then I look at the diameter of this subgraph in the random planar map, then Yu and Nina and Shin proved the existence of a growth exponent for this diameter. And they call it chi. And they conjecture that chi is equal to 1 over d. And in my work with Yuan, we show that indeed chi is equal to 1 over d. And so this is like maybe 95 or more % of the technical effort involved in this project, and like where a lot of interesting subtle arguments show up, but that will be beyond the scope of a 20-minute talk. Okay, so now we have these three ingredients, and now let me sketch how I can use these three ingredients to prove my result. So first, let me prove the upper bound. So again, by the first ingredient, instead of just considering a DLA, I can instead consider a loop race random walk. So if I run my loop race random walk for m steps, again, by the second ingredient, using Mullen's bijection, which it gives us an encoding in terms of a walk on Z2, I can show, using stuff about random walks, that I can cover this loop race random walk run until time n by m to the delta number of these subgraphs of triangles traced in intervals of time of length m squared. So we have m to the delta number of these time intervals of my random walk, each of these time intervals of length m squared, and together one can show that these cover the loop race random walk. And you could think of delta as just being small. And so now, by this theorem showing the existence of a growth exponent for the diameter of a subgraph, combined with our result identifying that growth exponent as 1 over d, one deduces that each of these subgraphs will have diameter that grows like m squared to the 1 over d, or m to the 2 over d. And so the diameter of this whole loop race random walk segment is at most on order m to the 2 over d plus delta. So again, I'm not showing all the technical details, but essentially this is the argument, showing the upper bound. Okay, and now to show my lower bound, again, I run my loop race random walk for m steps, and this time I'm going to again intersect it by m to the delta number of these subgraphs. Instead, this time I'll choose them to be disjoint, And rather, instead of covering the loop race random walk, I just want to intersect the loop race random walk by this number of subgraphs. And each subgraph will have, this time, m to the alpha triangles where alpha is smaller than 2. The way to think about this is alpha is smaller than 2, but alpha plus delta is as close as we want it to. So you have these intersections. And again, you can show that you can find such subgraphs, again, by translating to the language of random walk. And so now, I chose each of these subgraphs to have m to the alpha triangles. But in fact, again, by analyzing the random walk using like a Hufting's inequality, we can deduce that in fact each of these subgraphs will contain on order m to the alpha triangles, vertices of my random planar map. So each of these subgraphs which has m to the alpha triangles will also have on order m to the alpha vertices of the random planar map. Which means that if I look at a metric ball centered at my root to contain this loop race random walk and these subgraphs, well, this ball will contain at least as many vertices as all of these subgraphs, so at least on order m to the alpha plus delta vertices. And since, again, this d gives the growth exponent for the metric ball in the random planar map, that implies that the radius of this ball is at least on the order of m to the alpha plus delta over d. And so this gives us our lower bound. Okay, so this completes the proof. And now just a very quick remark about open questions. There are still a lot of questions that you can ask about DLA other than the growth exponent of its external diameter. Essentially all of these questions require some new insight. So these are a little bit far from being solved, but yeah, you can ask all these sorts of questions to analyze DLA further. Yeah, thank you.
Are there any questions?
So if you apply KPZ, I guess that tells you something about the should that tell you something about the dimension of DLA in the square lattice?
No. These DLA for different gamma are like very much different objects. So you can't kind of compare DLA in like a Euclidean lattice or something to DLA in the random in any way. Yeah, it doesn't work.
Because there's no conformal invariance for.
Correct.
Well, and because the set depends on the field, right? Somehow.
Like if you embed the planar map and you run DLA on the embedded map, then like the scaling limit should depend on the type of planar map that you're looking at. Like it won't be giving you it won't be like the same as the scaling limit of Euclidean DLA.
Isn't that just the same as saying there's no conformal invariance?
Yeah, essentially.
Yeah, we're also just saying that KPZ only works if the practical set is independent of the geometry, which is maybe the same as what you're saying. But yeah, okay. Yeah.
Any other questions? Yes, let's thank the speaker again.